Okay, so today's first speaker is Professor Omri Sarig from Weizmann Institute of Science. Here he will talk about stochastic properties for measures of maximal entropy for smooth surface diffeomorphisms. Let's welcome.
Okay, so thank you very much, and thank you all for coming despite this very early hour of the day. So I'm going to tell you today about joint work, which Jerome, Sylvain, and I were working on for quite a bit of time, 6 years, and finally it's over, and finally it's written, and it's on archive. It took us a long time. So these are my collaborators. This is Jerome Bouzy, and this is Sylvain Crovisier. And together what we were trying to do is to study the quantitative properties for general diffeomorphisms. Diffeomorphisms which are chaotic in the sense that they have positive topological entropy, but we're not going to assume anything else, like a Nosov or uniform hyperbolicity. So let me start with an outline of what we're going to talk about today. So we're going to assume the following setup. So M is going to be some closed smooth surface. F is going to be an infinitely differentiable diffeomorphism. The only chaos assumption we're going to make is positive topological entropy. And mu is going to be an ergodic measure of maximal entropy. So the existence of an ergodic measure of maximal entropy is not a restriction. This is such measures always exist in such situations because of a very important result of Newhouse. So let me put his name on the board, because this work, the existence of measures of maximal entropy for general diffeomorphisms, is in some sense the beginning of this entire line of investigation. Okay, so I emphasize that we're not going to make any other assumptions. Dimension 2 can be relaxed, but however, I'm going to, in this talk, only to talk about dimension 2 because the results are easier to state in this case. So what we would like to do, we would like to study certain quantitative properties of the measure. So what does that mean? It could mean many things. It could mean precise rates of mixing. It could mean distributional limit theorem for the Birkhoff sums. Some finer results like approximation of Brownian motion. It could mean effective intrinsic ergodicity estimates, various things. I'm going to state exactly what I mean by these results at the end of the talk. So I will give you full statements of exactly what these properties are and what exactly we can prove under this setup. Now I would like to emphasize that everything I'm going to talk about today is known if you assume that the diffeomorphism is an Nosov, okay, or axiom A, or has a Young tower with exponential tail. So if you add additional assumptions on the diffeomorphisms, then many of these results have been known for a very long time due to the works of many people, some of whose names are here on the board. What is new is the generality, okay? And in order to prove results of this type at this level of generality, we need a new idea, and this new idea is a new property called strong positive recurrence, which is strong enough to imply all these results and is weak enough to hold in this general setup. So what exactly is this new dynamical property, SPR? That's exactly the thing I'm going to focus in today's talk. That's the new thing. Okay, so how are we going to attack this problem? So the scheme is fairly standard. We are going to start with symbolic dynamics. So we have known for more than 10 years that diffeomorphisms at this level of generality possess countable Markov partitions. And we have also known for a long time that if you take the measure of maximal entropy and write it down in symbolic coordinates, then what you get is a Markov chain. Okay, it's a Markov chain. However, there is a twist. This is not a Markov chain with finitely many states, as in the Anosov case. It's a Markov chain with infinitely many states. And the problem with Markov chains with infinitely many states is that they do not all satisfy the properties I listed before. There are countable state Markov chains that mix much slower than exponential, polynomially. There are countable Markov states that don't satisfy the central limit theorem. They satisfy perhaps some stable limit theorem with a different distribution, or maybe nothing. So we need an additional property. We need an additional property of the Markov transition matrix to be able to deduce the quantitative results that we are aiming at. And this is exactly where the strong positive recurrence property enters the picture, because it's going to imply to us that the transition matrix of the Markov chain associated to the measure of maximal entropy has spectral gap. Okay, what exactly I mean by spectral gap, I will tell you later. Okay, it requires a precise definition. We'll do it later. I just want to say at this point on a very, very general level that the purpose of this strong positive recurrence property is exactly this, to guarantee that the transition matrix of the Markov chain, countable state Markov chain, which represents the measure of maximal entropy in symbolic coordinates, has spectral gap. Now what is nice is that this condition that guarantees spectral gap holds at very great generality. Okay, so once you know that the transition matrix satisfies the spectral gap, in a sense which I will explain in detail later on, once you have the spectral gap, then deducing all the results which I stated before, exponential decay of correlations, limit theorems, and so on, that's a more or less well-known thing. Okay, there is people have worked for 40, 50 years on and produced a very powerful set of tools which now are called the transfer operator method, which translate spectral gap for the transfer operator, in our case the Markov operator for the Markov chain, translate it to a vast array of very, very strong quantitative properties of the measure under investigation. Now, when you look at this program, so some parts are old and some parts are new. So as I mentioned before, the existence of Markov partitions for diffeomorphisms is known for already 10 years. I proved it in 2 dimensions, and Snir Ben-Ovadia proved it in any dimension. The fact that the measure of maximal entropy is coded by a Markov chain is also a very old thing, going back to the work of Bill Parry for subshifts of finite type, and the work of Boris Gurevich for countable state Markov chains. So this is already known. The last part, the application of the transfer operator method, is also something which is well known. It's the result of the work of many, many people, starting with Ruel in the dynamical context, who used it to prove exponential decay of correlations, and then Nagaev and Giversh and Hardy did limit theorems. Guezel did the almost sure invariance principle, approximation by Brownian motions. René Roux and me, we did effective intrinsic ergodicity. I'll tell you later what this means. And many, many other people, Polycott, Baladil, Liverani, Tsuji, many, many other people contributed. Keller contributed to this set of tools which translate spectral gap for the action of the transfer operator on some Banach space to the analysis of the underlying measure and its fine quantitative behavior. So the first step is known, the third step is known. What is not known, what is new is the middle step, this condition which implies spectral gap. So my plan for today's talk is to just review what is known about Markov partitions, what we need, okay, for our work. I'll review it. Then I will focus on what exactly this strong positive recurrence condition is, and I'm going to skip the transfer operator part, not because it's trivial, it's not trivial simply because it uses a toolbox that already existed. We just had to use it. Okay, so let's start with the first part of the program, symbolic dynamics. This, of course, is a very, very old idea in dynamical systems, starting with Adamar, brought to chaotic dynamics by Adler, Weiss, and Sinai. And I'm going to tell you now what is known for general diffeomorphisms, without assuming an also that's what I'm going to focus on. Let me start with some terminology, and especially what exactly I mean by a Markov shift, because that's going to be the symbolic model that we are going to use to code our systems. Basically, it's a subshift of finite type, but the set of states is countable. That's basically what it is, nothing more. So the notation I'm going to use is this. I'm always going to think about a Markov shift as something associated to a directed graph. So you start with a countable graph, so countably many vertices and edges with direction. And then you look at the set of paths on the graph. So a path, a bi-infinite path, is a sequence of vertices which are connected by edges going in the right direction. Okay, so this gives you a connection of bi-infinite sequences of symbols. It's clearly invariant under the action of the shift, and so we let the shift act on it. I will denote the shift by sigma, and there is a very natural metric. There are many metrics. What is more important for us is not the metric but the Borel sigma field, but that's the metric I'm going to use. And when I speak of a coding of diffeomorphism, because I'm not going to speak of a loss of case, there is a small twist. So let me explain to you what I mean. So for me, in this talk, the Markovian coding of a diffeomorphism means some map, that's the coding map, which goes from symbolic space, the set of paths on a Markov shift, into the manifold, which makes this diagram commute. Okay, so the dynamics below on the manifold is coded by the dynamics above on the shift, and pi is the map that links them, and this diagram commutes. When I speak of coding of measures, what I mean is you take the measure on the manifold and you lift it. You find a measure on symbolic space which projects to it under the coding map. So this is what I mean by a coding of a map, of a measure. Now what is the twist? The twist is that I cannot expect the coding to be surjective in the non-Anosov case, in the general case. And the reason is, let me show you this. I'm sure you're all familiar with this famous picture, numerical picture that we cannot perhaps prove, but that's what we believe is the case. You have a phase space, and we should expect in the general case mixed behavior. So there maybe are some elliptic islands where the dynamics is zero entropy, maybe even quasi-periodic. Markov shifts are not suitable for describing dynamics of this type. Okay, Markov shifts are built to describe dynamics with exponential sensitivity to initial conditions. So they are suitable for perhaps for describing the chaotic C, this set of initial conditions with the sensitivity to initial conditions, which lies between zones where you have a motion with zero entropy, but they are not suitable for describing all initial conditions, only part of them. Therefore, I'm not going to even try to code the dynamics on the entire manifold. I'm not going to do it with the Markov shift. That's not a suitable symbolic model. I'm only going to try to code the part of the manifold, the collection of initial conditions, which exhibit strong chaotic behavior. Now, in this talk, what this means precisely is that we are going to try to cover chi-hyperbolic measure. So what is a chi-hyperbolic measure? A chi-hyperbolic measure is a measure which is hyperbolic. This means that it has positive Lyapunov exponents and zero Lyapunov exponents, and chi is a bound which bounds them away from zero. So I will say that a measure is a chi-hyperbolic if some of its Lyapunov exponents are less than minus chi, some of its Lyapunov exponents are bigger than chi, but none are in between. Okay, so it's a hyperbolic of this type, and I want to cover sets of full measure for such measures. Okay, I'm not going to try to cover the entire manifold, so I want to emphasize this. Okay, so now let me tell you what is the general coding result that we have by now. So it works in any dimension and in lower regularity. So assume that you have C1 plus epsilon diffeomorphism, so the derivative map is only assumed to be Helder continuous. And let's fix some chi, which is positive. And here is the coding map. I proved it in 2 dimensions, and Snir Ben Ovadia extended it to any dimension. Okay, so here is the theorem. The theorem is that there exists a Markov shift and an equivariant Helder map. So equivariant means that this diagram commutes. And this map is almost everywhere finite to 1 and almost everywhere surjective. And now let me tell you what I mean by almost everywhere. Okay, so what I'm going to take a subset of symbolic space, this sigma sharp. This sigma sharp is made of all sequences that do not tend to infinity. So the positive part of the sequence has a symbol that repeats infinitely many times, and the negative part of the sequence has a symbol, perhaps a different symbol, that repeats infinitely many times. So this is a very, very big set from the point of view of ergodic theory because it contains the non-wandering set. So all shift invariant measures, probability measures, live on this set. So that's a very, very big set from the ergodic theoretic point of view. And what I would like is for the coding map, when you restrict it to this set, to be finite to 1. I'm not saying bounded to 1, I'm saying finite to 1. And I would like the image of this set to have full measure for all chi-hyperbolic measures. Because I remind you, I'm not going to aim at the surjective coding, because that's unreasonable. But I am going to aim at codings which cover a set of full measure for hyperbolic measures. So specifically for chi-hyperbolic measures. You can push chi to be as small as you want, but it has to be positive. Okay, so this is the coding map. What is the significance of finiteness to 1? The significance of finiteness to 1 is, I remind you, just a fact from ergodic theory, Abramov theorem. If you have a finite to 1 factor map, it preserves entropy. So if you start with the measure above and project it below, it will retain its entropy. Conversely, finite to 1 guarantees that if you have a measure below, you can lift it to a measure above with the same entropy. So this is the significance of finiteness to 1. It is not a countable set, so the set, each coordinate takes countably many values, but the set of all sequences has the cardinality of the continuum. Subsequence. It has a constant subsequence. Okay? I don't want, I'm omitting sequences that escape to infinity. Okay, that don't repeat any symbol. I only look at sequences which repeat some symbol infinitely many times, but they are not eventually constant. Exactly. Not divergent, exactly. Okay, so that's the theorem we are going to use. I'd like to say that there are many generalizations of this theorem today, especially due to Yuri Lima and his collaborators. So for example, Yuri Lima and Carlos Mateus have a version of this result for maps with singularities, like billiard maps. Yuri Lima and me, we have a version of this for three-dimensional flows. There, the symbolic model is suspension over a countable Markov shift.
This condition of constant substitution, this is what replaces compactness somehow.
It's still not compact.
It's not compact.
It's still not compact. You have a very good intuition. I'm going to get to something similar to this later on. You are onto something. Okay. There is a very, very general coding theorem I would like to mention by Araujo, Lima, and Poletti, which does even endomorphisms, non-invariant. There are also improvements of this result. For example, you can make the coding injective almost everywhere. That's due to Boyle and Bouzy. If you fix the measure, if you fix one measure, here we don't fix the measure. We look at all measures. And there is a version of the coding due to Ben Ovadia where you can calculate exactly the coded set. What is going to be useful for us is another improvement due to Jerome and Sylvain and me that says that if you restrict to a homoclinic class, then you can get an irreducible coding. You can get the graph to be connected. Okay, you can get a transitive coding. Okay, so we have this coding map, and I remind you that because the map is finite to 1, every measure below, for example, the measure of maximal entropy, has a lift above, has a measure above with the same entropy that projects to it. Okay, now I claim that the lift of exactly. So that's exactly the statement. There exists a lift. There exists a measure above. It's not a map, but you can construct a measure above that projects to the measure below. Basically, what you do, you use finiteness to 1 to average over the fibers, and then you get a measure above that projects to the measure below with the same entropy. That's important. Now, because if you start with the measure of maximal entropy and you lift, you get a measure with the same entropy. I claim that this measure is also a measure of maximal entropy. Why? Because if there were a measure with higher entropy above, then it would project to a measure with higher entropy below. Okay, so and that doesn't happen if this is the measure of maximal entropy. So the conclusion of this is that if you code the measure of maximal entropy below, what you get is a measure of maximal entropy above. And this makes us extremely happy. Why? Because whereas the measure of maximal entropy has no reasonable description in Riemannian coordinates, it has a very explicit description in symbolic coordinates. So this is this theorem of Bill Parry for subsets of finite type and Boris Gurevich for countable state Markov shift, which I mentioned before. And they calculated and found that if you have a transitive countable Markov shift, countable state Markov shifts, then its measure of maximal entropy is Markovian, is a Markov chain. Moreover, you know the transition matrix up to conjugacy. The transition matrix of this Markov chain is conjugate to the transition matrix of the graph. That's the Parry measure, the famous Parry measure. Okay, so we gain a lot. We started from something very, very amorphic, the measure of maximal entropy of a diffeomorphism. No, it's a singular measure, no description in Riemannian coordinates, but we ended up with a very, very concrete object, a countable state Markov chain, and we even know the transition matrix at least up to conjugacy. So that's the idea. Okay, so summary up to this point, it's a good idea to code the diffeomorphism by a Markov shift, and then the measure of maximal entropy becomes a very concrete thing. It's a Markov chain, and the transition matrix is a conjugate up to a scalar to the transition matrix of the graph. Of course, this is not enough to deduce the stochastic properties of the measure, because I remind you, countable state Markov chains have a huge variety of possible behaviors. Not all of them mix exponentially. Okay, we need something more, and what we need is this spectral gap, which I mentioned at the beginning of the talk. Okay, so what is this spectral gap that we need? We need to be careful because we are talking about an infinite matrix. Okay, we have no natural Hilbert space in the background on which this matrix acts. We need to be careful. So we need to state exactly what we mean by spectral gap. Okay, so some notation. So G, I remind you, is the graph. And I'm going to denote by T the transition matrix of the graph. So it's a matrix indexed by the states. And you have entry 1 at position AB if there is an edge from A to B. And if there is no edge from A to B, you have 0. Okay? So now I'm going to look at action on one-sided functions. So let's look at the one-sided shift. These are the one-sided paths on the graph. And a one-sided function is a function which depends only on the one-sided sequence of positive, non-negative coordinates. And I'm going to act on these functions using the Ruel operator. So the Ruel operator takes a function which depends only on the non-negative coordinates, and it sums it up on all possible predecessors. Okay? Now, you can ask, why does this sum converge? In general, it doesn't converge, but it is a fact that the symbolic codings for diffeomorphisms, every vertex has finite degree. So it's only a finite sum, 4 codings of diffeomorphisms. Okay. So what is the spectral gap property that we need? Informally, it is the existence of a good Banach space. I'll tell you what good means later, on which this operator acts with good spectral properties. Okay, I emphasize to all those people that are used to spectral gap in the context of Hilbert spaces, this is dynamics, smooth dynamics, there are no Hilbert spaces here, unfortunately. Okay, it's going to be on a Banach space. It actually means, in this case, finite going out and finite going in, yes. Both of them, yeah. Okay. So now let me state the spectral gap property in a formal way. So I would like, the spectral gap property is the assertion that there exists a Banach space for every parameter beta. There exists a Banach space of one-sided functions, functions which depend only on the non-negative coordinates, which has the following properties. First of all, it's a big space, so I would like it to contain all the indicators of cylinders. In particular, it should generate the entire Borel sigma algebra. Okay, I would like it to contain all the indicators of cylinders. I would like convergence in norm to imply at least uniform convergence on partition sets, on cylinders. Here is the main part. The operator has got to be bounded. It has got to preserve the space. It has got to be bounded. And its spectrum has to consist of an isolated simple eigenvalue at e to the entropy and a compact subset of the open disk. So the gap is the distance between this compact part and the simple pole. And because we are in the context of Banach spaces and not Hilbert spaces, there is no self-adjointness, nothing. It could be a big set here, okay? It's not necessarily a discrete set. Okay. It's very nice to have also some other functional theoretic properties. I'm going to put it as part of the definition. I would like to have the Banach algebra inequality. I would like to have the lattice inequality. And to do perturbation theory, it's very nice to have a situation that if you take a function and multiply it by a Helder continuous function, this is a bounded operation. Okay, so I would also like to have this inequality. So if you can construct a Banach space with these 7 properties, then I will say that we have the spectral gap property. And trust me that when I compiled this list, I did it so that you could apply all the methods of Ruel, Nagaev, Givar, Hardy, Rousseau-Hegel, Keller, Liverani, Guezel, and get everything that you want. Okay, so it's sort of an abstract thing that if you have a Banach space with all these properties, then you can start to operate a machine of all these great mathematicians and get whatever you want. Okay, so now what's the problem? The problem is that sometimes you do not have such a Banach space. Why? Because there are countable state Markov chains which do not satisfy the consequences, which do not mix exponentially. As soon as you have a Markov chain that doesn't mix exponentially, you know that you cannot construct a Banach space like this for its action. And there are situations where you have measures of maximal entropy which mix sub-exponentially. Not for diffeomorphism, but for general Markov shifts. Okay, so there is a question. When can you construct such a Banach space? And I already tell you, sometimes you cannot. Okay, so luckily, the question, when does there exist such a Banach space, is completely understood. So let me tell you now a necessary and sufficient condition on the graph for the existence of a Banach space of this type. Okay, necessary and sufficient. So so we have a graph. Now, the condition is going to be in terms of two combinatorial objects. The first one is the count, the number of all loops of length n at a fixed vertex. So A is a fixed vertex, and a loop is a path on the graph of length n that starts at the vertex and ends at the same vertex. That's a loop, and I'm going to call the number of these loops Zn. Now let's look at the special subset of first return loops. So these are loops that start at A and return to A for the first time after n steps. So here I count all paths of length n from A to A. Here I count all paths from A to A which do not pass through A in the middle. Okay? And now here is the theorem. It's a theorem by Van Sier and me that there exists a Banach space with all the properties I listed before, if and only if, you have the following condition, which is called the Weir-Jones condition, that for some vertex, in the transitive case, if it happens for one, it happens for all. For some vertex, this number grows exponentially faster than this number. Okay, so the exponential rate of growth of the count of all loops should be strictly bigger than the exponential rate of growth of the first return loops. Okay, so this is what is called today the strong positive recurrence condition for graphs, for Markov shifts. It's an extremely important condition in symbolic dynamics, and it's very funny. It was discovered by many people in different forms, which turn out to be equivalent. Sometimes the equivalent is not easy to see. Sometimes the equivalent is a deep theorem, but it turns out to be equivalent to many conditions that people used over the years to solve very different problems. Okay, so I'd like to mention some of these names. So the first one to have used this condition is David Weir-Jones in a very classical pair of papers from the end of the 60s, which is basically a generalization of the Perron-Frobenius theorem to positive matrices, infinite positive matrices. That's a fundamental paper in all this business, and that is where this condition appeared for the first time. Then this condition was used by Gurevich and Zargarian and Gurevich and Savchenko for solving, in fact, a stability problem in the theory of equilibrium measures, and I used it when I studied phase transitions. Our conditions were different. It took some time to realize that they are all equivalent to this condition. So this is a very important condition in symbolic dynamics, in the theory of countable state Markov chains, and it turns out that it also nails the spectral gap property, the existence of a Banach space with all these spectral properties. I'd like to mention now another characterization, another equivalent formulation of this condition due to Sylvie Rouet. This is not Rouel, this is Rouet, Sylvie Rouet. And she proved something which is going to be very important for us. She proved that Weir-Jones's condition holds if and only if the entropy at infinity is strictly smaller than the full topological entropy. Okay, so the entropy at infinity is the lim sup of the entropies as the measure tends to infinity. I will tell you what it means. Okay, but I just like to say at this point that it turns out that Weir-Jones's condition, which is necessary and sufficient condition for the existence of a Banach space with all those properties, is also equivalent to entropy gap at infinity. Okay, so now what is exactly entropy at infinity? So what does it mean? What does it mean to take lim sup of the entropy as the measure tends to infinity? So I remind you that we are talking about graphs with finite degrees. Therefore, the set of sequences is locally compact. Okay, and it's natural to say that a sequence of measures tends to infinity if it leaves every pre-compact set. So you take a pre-compact set, okay, then eventually most of the mass will leave that set. So in quantifiers, for every pre-compact set and for every epsilon, there is a position in the sequence whenceforth the mass of this pre-compact set is small. Okay, so the mass eventually leaves every compact set. It's anti-tightness, the opposite of tightness. Okay, so now it's clear how to define lim sup. What you do is you look at all sequences of measures which tend to infinity in this sense, and you look at the lim sup of their entropies, and you take the supremum over all sequences, and that's the lim sup.
Every sequence has eventually small measure?
No. It's the opposite of tightness. You take a compact set in the shift, then eventually most of the mass will be outside. So these are going to be invariant measures, so they will be recurrent. Eventually, yeah, every cylinder will eventually have small measure. Yeah. Yeah, yeah. Okay. So now, summary up to this point. What we need to know to get the spectral gap property, we need to know that we have entropy gap at infinity, because then we can use the theorem of Sylvie-Rouet to know that the condition of Weir-Jones holds, and then we know if the condition of Weir-Jones holds, we know that we can construct a Banach space with spectral gap.
So this condition is easier to apply than the main condition, the number of points.
I think it depends. I think it depends on the example. I think it depends on the example. But yes, yes, yes. Patience, patience. All will be revealed. I just like to say at this point that this idea of entropy gap at infinity seems to be a very, very important condition when you study dynamics on non-compact spaces. It has appeared in in the works of other people, other contexts. I'm going to mention some names. So in the theory of interval maps, it was used by Jérôme and Sylvie. There is a very nice paper, very beautiful paper by Yomi, Todd, and Velozzo, where they use this condition to study upper semi-continuity of the entropy function on Markov shifts. It was used in homogeneous dynamics, for example, on the modular surface in a famous paper by Einsiedler, Lindenstrauss, Michel, and Venkatesh. There are results on other non-compact manifolds, even with the variable negative curvature. I'd like to mention works by Pitt and Shapira, Barbara Shapira, Guezel, Nu, Shapira, Tapie, and Riquelme. And somebody told me that Nu is not a real person, but I'm not sure about that. Yeah. If Nu is a real person, I apologize. And I'd also like to mention another condition, that the pressure on the singular set is smaller than the full pressure, which appears in the work of von Klimenhager and Dan Thompson, in the work on generalized specification properties. And it's on the heuristic level, it's a very similar condition. Okay, so now let's go back to manifolds and diffeomorphisms. Okay, and obviously, what we need to do is we need to find a general dynamical property which guarantees that you have a symbolic model with spectral gap. So a symbolic model with entropy gap at infinity. And now there is, something which obviously we need to do. We need to understand what does the condition of entropy gap at infinity for the symbolic model, what does it mean on the manifold? Now, this is a little bit confusing. Why is it confusing? Because the Markov shift is not compact, so it's clear what it means to escape to infinity, but the manifold is compact. So how are you going to escape to infinity on a compact manifold? So here is the answer, and this in some sense is one of the important things to understand in this business. So what you should look at is not escape to infinity on the manifold. What you should look at is on the subset of initial conditions with positive Lyapunov exponents. That's a horrible non-compact set, and look at convergence at infinity on this set. Okay, and that's the secret. So what you have to do is not think about the manifold, which is compact. You should think about the chaotic C. Okay, there is a grading of the chaotic C by passing sets, and you should think about escape to infinity in terms of escaping passing sets. So exactly what this means I will tell you. But since I'm going to talk not about the entire manifold, but I'm going to talk about the chaotic C, okay, the set of initial conditions with exponential sensitivity to initial conditions. I've just now moved from the heaven of a smooth manifold to the hell of a Borel set with empty interior and no visible topological properties whatsoever. So now I'm in a measurable space, really measurable space, okay? The set of initial conditions with non-zero Lyapunov exponents. So I need to have a structure on this set and speak that will allow me to talk about convergence to infinity. We need something because this set is possibly all boundary. I don't want to say that it's all infinity. Okay. So what are we going to do? So we are going to use some terminology which is abstract, but it's not too bad. Okay. It's basically something called Bornology. So what is Bornology? It's structure on an abstract space that allows you to describe escape to infinity. Okay. So the idea is that you define a class of sets that you call bounded sets, and you define escape to infinity as escaping all the bounded sets. Now, this collection of bounded sets, it has to satisfy some axioms. So let me tell you what are these axioms. I think they're all reasonable axioms. First axiom is that every point is bounded. Second axiom is that a finite union of bounded sets is bounded. Third axiom is that a subset of a bounded set is bounded. And the fourth axiom, it's the only one with substance, is that every bounded set is inside a measurable bounded set. We, of course, are thinking about the closure. Okay? So these are the four axioms. And if you have these four axioms, you have a collection of sets, which you can call bounded sets. And you can use it to define escape to infinity in the same way as before. A sequence of measures escapes to infinity with respect to this Bornology if for every small parameter epsilon, there is a position in the sequence whenceforth the measure of this bounded set is small. Okay? So example number one, typical example, you have a locally compact topological space, for example, a Markov shift. You look at the Bornology of pre-compact sets. Why did I say Bornology of pre-compact sets and not compact sets? Because of the axiom that every subset of a bounded set is a bounded set. Not every subset of a compact set is a compact set. Okay? So this is that's the classical example of a Bornology. Now, what is the Bornology we are going to use? It comes from Pessin theory. Okay? So let's assume that you have a diffeomorphism on a surface, and let's fix two parameters chi and epsilon. This is unfortunate, but we don't know how to bypass it. You have to fix some parameters, and look at the collection of all initial conditions, which have Lyapunov exponents, some positive, bigger than chi, some negative, less than chi, and none in between. I'm also going to assume Lyapunov regularity. Lyapunov regularity means that the conclusion of Oseledet's theorem holds. So you have the Oseledet's splitting and everything, all this sort of stuff. Okay, so this is a Borel set. It's a big set. It will have full measure for every chi-hyperbolic measure by the Oseledet's theorem. But it's a very bad topologically. It's just a Borel set. What is the Pessin Bornology? A set is bounded if it's inside the Pessin set with these parameters. Okay, now I have to remind you what are Pessin sets. So this is a little bit unfortunate because if you know what are Pessin sets, you don't need me to remind you what are Pessin sets. And if you don't know what are Pessin sets, then you will not understand what they are after I tell you fast. Okay, so but basically Pessin sets are sets where you have non-invariant sets, non-invariant closed sets, where you have uniform hyperbolicity. Okay, so this uniform hyperbolicity is described in terms of several inequalities. So C is the parameter associated with the Pessin set, but it varies. Okay, before we jump, you're very fast. But let's get to C in a minute. So the Pessin set, first property of Pessin set is that it has oscillated splitting. You can split a tangent space to an unstable direction and stable direction, two linear spaces. Let's do it step by step. So that's you have oscillated splitting. On the stable direction, vectors decay exponentially fast, and the parameter key tells you how fast they decay. But there is a constant in front. Okay? This constant in front doesn't depend on n. So as you look at the behavior of the in time, what happens to a stable vector as you iterate f again and again and again, the norm decays exponentially at the rate of chi, and there is a constant in front. Similarly, if you have an unstable vector, you have decay but in the past when you apply f inverse, so the decay is at an exponential rate but in the past. And there is a bound from below on the angle between the two. Now, what is this k? This k, that's the great idea of Pessin, is this, you look at what happens as you move down the orbit. So you compare the uniform hyperbolicity estimates at x to the uniform hyperbolicity estimates at f of x, f squared of x, f cubed of x, and on a Pessin set, you allow them to deteriorate, but they also deteriorate at a controlled rate, and the second parameter epsilon tells you the rate of decay of the constant. Okay, so this is a Pessin set. It's a fundamental fact in Pessin theory that the union of Pessin sets covers a set of full measure for all chi-hyperbolic measures. So this is, if you want, a gradation, a grading of the set of non-uniformly hyperbolic initial conditions which are chi-hyperbolic. And we are going to use this collection of sets as our Bornology. Okay, so we will work on the set of Lyapunov regular initial conditions which are chi-hyperbolic. And the Bornology we are going to use on this Borel set is the Bornology made, a set is bounded if it's a subset of Pessin set. Of course, everything depends on these parameters chi and epsilon. That's unfortunate, but we don't know how to avoid it. What? There exists a C. You can let C tend to infinity. As you let C tend to infinity, you feel more and more of your space.
You can include C and take union rules.
But then it will not be a passing set. But yes, if you take the union over all C, you get a set of full measure. Exactly, increasing C, that's in some sense escape to infinity with respect to this boundology is exactly that the mass moves to the part of the space where the optimal C is big. That's exactly what it means. Okay, so here is the definition of the strong positive recurrence condition. For a diffeomorphism, we will say that it's strongly positive recurrent if there exists a parameter chi such that for all epsilon sufficiently small, if you use the passing boundology with these parameters, you get entropy gap at infinity.
Chi and epsilon are fixed, and now you change C, you have then
No. A passing set is a set for which there exists a C, and you look at all passing sets, so all C's, all possible C's. Every C, for each C, you can look at a set of points which satisfy these conditions. This is a closed set, that's a passing set. Chi and epsilon are fixed. So the SPR property is that there exists a chi such that for all epsilon, if you work with the fixed chi epsilon, with the boundology with these fixed chi epsilon parameters, you have entropy gap. For all chi, there exists an epsilon. Okay, and these statements really depend on chi epsilon. Okay, so this is our condition. Okay, so now let's compare. So we have the SPR property, entropy gap with respect to the entropy gap with respect to the boundology of passive sets, and we have the entropy gap appearing in symbolic dynamics as a necessary and sufficient condition for the spectral gap property. Sorry, there was a question. Yes, going to infinity. Yes, exactly. Escaping. So mu tend to infinity in here means that the mass of the measure is chi-hyperbolic, so it all sits on chi-hyperbolic initial conditions, but it moves to parts of this set where the optimal constant in the passing set becomes bigger and bigger. So the hyperbolicity estimates becomes worse and worse. You need to wait a longer time to see hyperbolicity starting to appear. It's an invariant measure, yeah. Invariant probability measure, yes. Okay, so the difference between, so it looks similar, you have entropy gap here, you have entropy gap here, but what's the difference is the boundology. Okay, here you are escaping to infinity with the natural boundology on the Markov shift, which is the boundology of pre-compact sets. And here you are moving to infinity on the manifold with respect to the boundology of passing sets. And of course the question is, what's the connection? Okay, so if you want to know that an SPR diffeomorphism has a coding with spectral gap, you need to be able to deduce entropy gap above from entropy gap below, but these use different boundologies, so you need to be able to relate the boundology of passing sets to the boundology of pre-compact sets. Okay, so here comes the technical lemma, and the technical lemma is that you can construct. It's not true for all symbolic models, but you can construct a symbolic model where there is compatibility of boundologies. So this is the lemma. It's a little bit unreadable, so I'll just tell you what it means intuitively. It says that there exists a symbolic coding, so there exists a Markov shift with a factor map, such that it has these finite to one properties, which we need to preserve entropy, and it has this unreadable set theoretic condition, which is there to imply that if you have a sequence of measures which escapes to infinity above, then its projections escape to infinity below. Okay, so so there exists a symbolic model with all the finiteness to one that you need to preserve entropy, such that you have compatibility of boundologies in the sense that if you have a sequence of measures which escape to infinity on the Markov shift, then its projections escape to infinity on the manifold below. Okay, so now it's just a matter of chasing definitions to see that if you have an SPR diffeomorphism and you use that symbolic coding, then you get spectral gap. So I have the proof, but I'm going to skip it because it's just chasing definitions. So I'd like to move to the third part because of time, and just tell you what you can get out of this. No, I have no idea how to. No, you have to construct it. That's the work. It's a particular coding. Yeah. Yeah. Okay. Are there?
No, spectral gap is you construct on some space. Like it's difficult to say. You don't.
Because I was wondering, you know, if you have one coding, this implies exponential mixing for the manifolds.
Okay. So the codings that we construct have other properties which enter the proof, which are very important. And if these properties hold, then we can prove that the diffeomorphism is SPR. So in some sense, the existence of a coding is equivalent to SPR property if you add some other technical properties for the coding, which I did not list. But in general, I mean, the collection of possible codings is enormous. I mean, I don't think it's reasonable to ask something about all coding. Absolutely. Absolutely. If in dimension 3 you have examples where all measures have zero Lyapunov exponents, and none of them are chi-hyperbolic, and nothing that I've said applies to it. But there are examples in dimension 3, and maybe I will mention it at the end, for which this theory does apply.
Actually, we can find an example where mixing is just because of one-dimensional.
Absolutely. Higher dimension, there are other possibilities. For example, it follows from the existence of a symbolic model that the measure of maximal entropy is isomorphic to Bernoulli times cyclic permutation. Okay, so in the mixing case, that is always Bernoulli. But there are higher dimensional examples where the measure of maximal entropy is non-trivial Pinsker factor, you know, a loss of times rotation. So sure, in higher dimension, it's not always true. It cannot be always be true. But if it's okay, maybe I just, because I'm a little bit pressed for time, so maybe I will use my prerogative as a speaker to, because I want at least to show you what you can get from all this. Okay, first, before I can even show you what you can get from this, I have to tell you how you check this property. Okay, how do you know that the SPR property holds? So I'll just state dynamical criteria which you can check in examples. Okay, so here is the criterion that works. So suppose you have a C1 surface diffeomorphism, and assume that it has the following dynamical property, that the Lyapunov exponent as a function of the measure behaves continuously on sequences of measures whose entropies tend to the maximal entropy. So in general, the Lyapunov exponent is not continuous as a function of the measure, but if you have the property that for all sequences of measures whose entropies converge to the topological entropy, the Lyapunov exponent behaves continuously, then the map is SPR. Okay, that's a sufficient condition. And what is nice is that you can using Yomdin theory, you can check this condition. Okay, so we proved a few years ago that if you have a C infinity surface diffeomorphism with positive topological entropy, then you have this continuity property. And therefore you are always SPR. So this is the reason why this condition holds in such great generality, because this entropy continuity property holds in great generality. C infinity gives it. In fact, recently David Bourget has extended this result, generalized it to CR diffeomorphisms. And he proved that whenever you have a CR surface diffeomorphism, which satisfies this inequality, so lambda max is the asymptotic Lipschitz constant of the map. So this is the asymptotic Lipschitz constant of the map. So if you have this inequality, that the topological entropy is bigger than the asymptotic Lipschitz constant divided by the number of derivatives, then your entropy continues. You have this continuity property of Lyapunov exponents. Therefore, by the results I mentioned before, you are SPR. So you see that SPR holds in a very high generality. By the way, you can see how nice Bourget's result is. As R tends to infinity, this becomes 0, and you get our result. Okay, so it's a very nice way to extend the C infinity result to finite regularity. Okay, so this slide is just meant to tell you that this is a condition that you can check for many examples. Okay, so summary up to here. C infinity surface diffeomorphisms are entropy continuous. Even CR diffeomorphisms with sufficiently high entropy are entropy continuous. Therefore, they are SPR by the result I mentioned before, and therefore there exist symbolic models with spectral gap. Okay, so now we're at a position where we can crank the machine and start turning the wheels and get consequences. So I'll just mention a few, probably not all of them, beginning with the exponential decay of correlations. So I'm going to talk about Helder observables. So a Helder function, I remind you, is a function such that you have this modulus of continuity. And I'm going to use this notation for the norm. And the theorem is as follows. Imagine that you have an ergodic measure of maximal entropy. Problem, it's not always mixing. Maybe there is a cycle. But what is true is that the measure is always isomorphic to Bernoulli times the cyclic permutation of p points. That comes very easily from the symbolic description. And if this is the case, what you can do, you can take f to the power p. If you take f to the power p, you kill the cyclic permutation. The measure has p ergodic components, each of which is mixing. So you can do decay of correlations for the ergodic components and get exponential decay. Okay? If you know in addition that the measure is mixing, then you don't need all this spiel, all this game, and you can just get exponential decay of correlations for the measure. Okay, so this is an example. Okay, another result, approximation by Brownian motion. What I want to do now is this. I pick an initial condition. I look at the graph of the Birkhoff sums as a function of n. I get this random walk driven by the dynamical system. Now I want to scale the x-axis by n and scale the space by square root of n and say that the result looks like the path of a Brownian path. Okay, so this is called the strong almost sure invariance principle. And to state this formally, you need the language of coupling. So here it is. So now we look at the Birkhoff sums as you fix the initial condition and you look at the Birkhoff sums as functions of n. And the statement is that you can construct a probability space with two stochastic processes defined on the same space, such that the first process is equal in distribution to the Birkhoff sums. So you cannot use the methods of statistics to distinguish this process from the process of Birkhoff sums. And the second process is Brownian motion. And the two processes are pointwise close. So the difference between them is little O of n to the lambda, where lambda is less than 1/2. So this is very good because when you do the scaling, you divide by square root of n, this thing tends to 0. So you get convergence to Brownian motion. So of course this implies many things. It implies the central limits theorem, and it implies, for example, the law of the iterated logarithm. So maybe I should explain what it is. So this is these are not Birkhoff sums of dynamical systems, but let's imagine that they are. So imagine that you pick many initial conditions at random, and you draw the graph, the random walks that they produce when you look at their Birkhoff sums. So the statement is that these paths tend to remain inside some deterministic envelope. It's these two black lines here, and the law of the iterated logarithm tells you what is the formula of these lines. Square root of it's a constant times square root of t log t. That's why it's called the iterated logarithm. So here is the statement. You have some Helder continuous observable which is centered, not a boundary. Then if you look at the Birkhoff sums and divide by a little bit more than n log n, it converges to 0. If you divide by a little bit less than n log n, there is a subsequence that goes to infinity. So the critical bound is constant times square root of t log t, and it's also true for the bottom side. So in fact, what the path does, it oscillates infinitely. Typical path does it oscillates infinitely many often between this curve and this curve. Okay, that follows from the almost sure invariant principle automatically, almost automatically. Okay, I'm gonna skip this. I'm gonna skip all this. Oh, I'm gonna skip this and mention this because, yeah, and then I'll end. So I want to tell you what is this effective intrinsic ergodicity that I mentioned at the beginning of the lecture. It's a stability property of the measure of maximal entropy, and it works in the following way. You take a measure whose entropy is nearly maximal, and you want to say that this measure has to be close to the measure of maximal entropy. So again, I take a measure which is not the measure of maximal entropy, but its entropy is nearly maximal, and I want to say that this measure has got to be close to the measure of maximal entropy, and I want to quantify the distance. How do you quantify the distance between two measures? You compare them on test functions. Okay? Basically, what I'm going to show you is a result that says that if the entropy of the measure is epsilon close to the maximum, then when you compare the two measures on Helder continuous test functions, the difference is square root of epsilon times a constant. Okay, so it's okay. So here is the statement. And now it's important that the diffeomorphism is transitive or that you restrict to a homoclinic class, because I want to have a unique measure of maximal entropy to look at. And the statement is that there is a constant such that for every beta Helder continuous function psi, if the entropy of M, that's an arbitrary measure, if the entropy of M is epsilon close to the entropy of the MME, of the measure of maximal entropy, so M is nearly the measure of maximal entropy, this difference is epsilon, then the difference between the measures when you evaluate them on test functions is square root of epsilon. Okay? It's also true for Lyapunov exponents. The Lyapunov exponents of the measure also have to be square root of epsilon close. All the results I've shown you so far are all known for anodes of diffeomorphisms. I forgot to say it. Okay, decay of correlations was proved by Ruel, for example. The almost sure invariance principle was proved by Denker and Philip. Okay, what else have I shown you? I forgot. CLT was proved by Givers and Hardy. Okay, everything is known for anosov. In this, I forgot to say it. This. Okay, maybe Sinai before. Okay, maybe Sinai before. This intrinsic ergodicity was proved for anosov diffeomorphism by Shirali Kadyrov. Okay. Thank you. You are right. Yeah, Givers and Hardy is locally material, not centrally material. Yes. Yes. Thank you. Okay, so nearly out of time. I'll skip some other things, and thank you very much, and congratulations to all the award winners.
Thank you very much for the very great talk. Okay, any questions or comments?
So a very simple one. Where did you use dimension 2 surface?
So I use dimension. Okay, I use dimension 2 for this for entropy continuity. Okay, so I had the criterion for SPR, which was that I have that the Lyapunov exponent behaves continuously on sequences of measures with entropy tending to the maximum. So this property does not hold in general. I'm using C infinity and dimension 2 and Yomdin theory in dimension 2 to prove it. So this is where dimension 2.
But you said it can be generalized. Okay?
Not this.
Not this. Other approach.
What can be generalized is that if you assume that the diffeomorphism has the strong positive recurrence condition, which sometimes holds for other reasons, for high dimensional example, then you can get all the results that I mentioned
before. What about continuity with respect to diffeomorphisms?
So in this example, you also have continuity with respect to the diffeomorphism. So if you take a sequence of diffeomorphisms that converges to a limiting diffeomorphism, and you take a sequence of invariant measures for each diffeomorphism, and you have these limits, then you have the Lyapunov exponent converge. It's also true for continuity with respect to
measure of maximal entropy is continuous with respect to diffeomorphism?
Oh, the measure of maximal entropy itself, I don't know.
Okay, I'm gonna ask a question which will show that I didn't follow the details. I actually have 3 questions, and you can maybe ignore the first 2. So I wanted to ask, like, where do you really need smoothness? In the sense that I see that your spectral SPR condition, you could imagine it as a condition on a fiber bundle instead of on a tangent bundle. And then my second question would be, like, do you even need the map, underlying map F, to be even continuous? And then my third question, that's the key question, is that how do you fit this for the, say, natural extension of the Gauss map. It seems like
Yes.
yeah, that's my question.
Yes. Okay. Where do I need smoothness? I will split my answer into two parts. There are two types of smoothness that are used here for different purposes. The first type of smoothness I cannot do without at all is C1 plus epsilon. Okay, that the diffeomorphism is Helder continuous. This is needed to apply Pessin theory. And I need to use Pessin theory to construct the countable Markov partition, out of which I get the symbolic coding. Okay? If you tell me that you have a diffeomorphism in any dimension, which is C1 plus epsilon, and you also tell me that it is SPR, then everything works without any additional smoothness requirements. If you don't tell me the diffeomorphism is SPR, I need to prove that it is SPR. And then I need to check this entropy continuity condition. And this uses smoothness in a very, very heavy way because it's based on Yomdil theory. Now, just to push this point a little bit further, there are examples in dimension 4 by Misiurevich and in dimension 2 by Jerome Bouzy of diffeomorphisms with finite degree of regularity, which do not have a measure of maximal entropy at all. Okay? So you cannot throw away smoothness out of the window. Now, about the Baker transformation, if you have uniform hyperbolicity, then you have a finite Markov partition. And this is sufficient to get everything basically from thermodynamic formalism from the work of Ruel and Bowen. Ruel and Bowen. Yeah. Then you have a finite Markov partition.
Is it possible to extend the theory to setting of random maps, random C infinity diffeomorphisms?
That's a wonderful question. You should ask Diva. Finding Markov partition for random maps, I think, has not been done yet. Yeah.
So, any other questions or comments?
So why do you work with chronology and this Pessin set, like the strong positive recurrence? The way I think it's nicely visualized is you take a ball and you look at return sets and like the first return time versus all return times up to time n, and you want the number to be like the original definition you had. Isn't that it's impossible to work with?
It's not a ball. It's not a ball. So what is important for me? Okay. Maybe I'll show you another. I'll use Adam's question to steal another minute from your time. You can take a Pessin set and ask about the return time to the Pessin set. Okay. So what is important is if you want to build a Young tower, for example, is that this function, which is unbounded, should have an exponential tail. But it's a Pessin set, not a ball. Okay? In fact, it follows from SPR that the return time has exponential tail, and it follows from this that you have a Young tower with exponential tail. However, it's better than a Young tower in the sense that in a general Young tower, the projection from the tower to the map is infinite to 1. Here, the projection from the tower to the map to the manifold is finite 1.
Okay. Oh.
Sorry? Okay, so one of the nice things about the strong positive recurrence condition on a Markov shift is that it gives you stability for the existence of an equilibrium state under perturbation. So if you have an equilibrium state for the constant potential, for the zero potential, that's the measure of maximal entropy, and you know that you are strongly positively recurrent, then you know that there is also an equilibrium state with all the stochastic properties I mentioned before for all small L infinity perturbations, Helder perturbations which are close in L infinity. Okay, so you do get equilibrium states for what's called small potentials. For other potentials, not necessarily. For example, there are examples of C infinity diffeomorphisms where the smooth measure mixes polynomially fast, not exponentially fast. So this would be so in this language, in the language of potentials, if you take the geometric potential, it is not SPR. But if you take the geometric potential and multiply it by delta, and delta is sufficiently small, it will be SPR. So somewhere along the line, there will be a phase transition. But what exactly happens for big potentials is unknown.
So sorry, the time is running out, so please ask him privately later. So sorry for that. Okay, so let's thank the speaker again.